Hi, my name is Ali Shirsavar from Biricha Digital. I recently came across a video by ElectroBOOM whereby he described how an induction motor works. As always, it was great fun and very educational. Mehdi, if you're watching, I'm a fan. Unfortunately, the little motor that he built at the end did not work, and I know how to fix it because when I was young, I actually made the same thing for my students in England. So in this video, we're going to talk about induction motors. We're going to talk about exactly how they function, and then I have made a little motor that I'm going to show you in the lab, and we're going to try and make it spin. Okay, so first let us quickly describe how an induction motor works. Let us say that I have three electromagnets and I place these physically 120 degrees apart from each other. Now, we know from university engineering classes that if I energize these three magnets with three-phase currents, which are 120 degrees apart electrically, then I get a rotating magnetic field. It's a bit like putting a north here, let's say, and a south here, and rotating this physical magnet around, right? But I'm not obviously doing it with a permanent magnet. I'm electrically generating this, but it's very similar to having a permanent magnet which I am spinning like that. It follows therefore that I've got a rotating magnetic field. If I put a permanent magnet rotor in the middle, it will start locking with this and spinning, and that's a synchronous motor. If I put a loop of wire there you go, let's say that a loop of wire comes out of the board, goes back into the board. Then, if you remember from school level physics, if we got a wire and we moved it around in a magnetic field, it induced a voltage in it. Okay, so I've got Fleming's right-hand rule, which was the generating. And he went by first finger field, second finger current, thumb, the movement of the wire with respect to the magnet. So if I do that, first finger field, thumb is the movement of wire with respect to the magnet, and therefore on this one, the induced current is going to be going into the board, and therefore on this one is going to be coming out of the board. Okay. Now, also remember from school level physics that using right-hand screw rule, we would know the direction of the magnetic field lines around a cable. So here it is coming out of the board. If I hold it, this is the direction of the current. This is the way my fingers are curling. So I am going to get magnetic field lines that is going that way. And then the same thing will happen on this one. It's going into the board. It's going that way and that way. Okay, good. Now let's draw a few more. So the induced current in this is actually creating its own magnetic field. And again, if you remember from school level physics, magnetic field lines came out of the north pole of the magnet and went into the south pole. So effectively what I've created myself is this. I have north here because magnetic field lines are coming out. I've got south here because magnetic fields are going in. I've got one rotating magnetic field there. I have got another magnet that I've induced, created by induction, and this magnet is going to follow that magnet and therefore is going to spin. And that's how an induction motor works. Okay, so then we're going to go to the lab and have a look at a little one that I've made, and then we're also going to answer some of the questions that came up in ElectroBOOM's the video. So here I have got my little motor that I've made, and I've only made a few small changes. First of all, I have massively increased the number of turns, and I did that not by winding it by hand. I actually bought some relays which have got thousands of turns of very fine wire, machine wound, and I basically butchered them out of relays. So I've got a lot more turns, and if you remember, magnetomotive force is in amp turns. So the more turns I have, the lower my current, but the bigger I can have a lower current for the same magnetomotive force. And the other thing that I've done is that instead of just having a electromagnet there, I have placed one opposing each other. So I've got one electromagnet here. Let's do that in green so that we see it there, and then another one there. And let's say if that would be a north, there will be a south, and therefore magnetic field lines will go straight through. And therefore you can see that I have got both more turns and I've got more magnets, and I have got an inverter chip, so I can impress a lot more current into these coils. So let us go to the lab and let us show this in action and also answer some of the questions that came up in ElectroBOOM's video. Okay, so this is my lab setup. This is something actually I designed in the 1990s in order to teach motor control. And I have got my 3 phases. As I mentioned earlier on, I've got 2 magnets. One is, let's say, for north and the other one for south. Flux is going, let's say, this way. Many windings because I took this out of relays. Then I'm generating a 3-phase voltage waveform with just a simple 555 and some logic gates. It's actually a square wave. Yes, it's not a beautiful sine wave, it's just got some extra harmonics, but it actually will work. And then I have got a 3-phase inverter chip here that takes the voltage signal and basically puts a lot of current across these coils, and we're going to show that on the scope in a bit. So let us do a close-up, and I will show you how the rotating magnetic field works, and we do a synchronous motor and then an induction motor. First, let us see if you've got a rotating magnetic field. So I have got here a permanent magnet, and I'm going to put that in there just to prove the concept that I have got a rotating magnetic field. And then I'm going to, there we go, it is spinning. The 3-phase control signals is going to this 3-phase inverter chip, which is basically putting some real current behind it. And you can see that this is rotating the permanent magnet to prove that I have got a rotating magnetic field there. I can change the speed by increasing the rate at which this rotating magnetic field is moving. And you can see that my synchronous, this is a synchronous motor, is spinning now quite nicely. Now let us change the rotor and put in just an aluminium rotor. In a real induction motor, we have aluminium bars covered in laminated iron. I will talk about that a little bit later, but for now, just a chunk of aluminium will hopefully move. Note that aluminium is not magnetic. It does not stick to my permanent magnet, so if it's going to spin, then it's by induction rather than by having permanent magnets. So now I have got the aluminium rotor, and I can turn on the rotating magnetic field. At the moment, this is going quite slowly, and I can increase the speed of rotation of my magnetic field. And you can see that as I do that, the rotor will start spinning a little bit faster and faster. I am spinning this faster and faster using my electronics, and of course the mechanics will follow. And I have an induction motor. Finally, let us quickly look at the screen in order to see the waveforms. Okay, so what I have here now is the top three channels are the voltage signal. You can see that is 3-phase. Yes, as I mentioned, it's only a square. It's not even PWM, but you can see that the current, the blue trace, which is current, is kind of taking a sinusoidal shape, and that is the current only in just one phase. If I had 3 current probes, you could see that those currents would also be 120 degrees apart from each other. And at the end, let us just answer a few of the questions that came up during ElectroBOOM's video. Here is a real induction motor. This is my stator winding. This is my rotor. Now the rotor bars where the big current is induced are inside as copper aluminium, and they're slightly angled. And the reason they're slightly angled is because the stator teeth, I don't know if you can see or not, the stator teeth are completely straight. And if these were also completely straight, then they would align with each other and you would get a jerky movement, which is called cogging. So by slightly tilting them, then it ensures that these rotor bars do not align directly with these stator slots that I have here. And then aluminium, as I showed earlier on, it's not ferromagnetic. So magnetic field lines will not go through very nicely. So we usually then put laminated sheets of iron with a very thin insulated paint on them, and they are done in this direction so that eddy currents cannot flow. So it minimizes the amount of eddy currents whilst it actually allows the magnetic flux line to actually flow through so that it can link from one side of the stator to the other bit of the stator. So there we go. That is the end of the video. Hope you enjoyed it. We run workshops on power supply design and EMC, not motor control. So if you're interested in power supply design or EMC, I hope to see you at one of our workshops.